It's a pleasure to be here in person, Q2B, see you all, and tell you a little more about Quantinuum's H series trapped ion quantum computer powered by Honeywell. We'll also have Jeff Henshaw here today, Director of Azure Quantum Business Development. Azure Quantum has been a great partner for Quantinuum and also for Honeywell Quantum Solutions before we were Quantinuum. We'd love to have him tell us a little more about the Azure Quantum a little later in the talk. So yesterday we heard from Ilyas Khan and Tony Utley about our new company, our vision for Quantinuum. We really are merging this state-of-the-art software, quantum software with the best high-performance quantum computing hardware. And we're hardware and platform agnostic, which means our software will run on various hardware platforms, both from Quantinuum's H series, but also from various other hardware suppliers and as well as simulators. And our hardware is also compatible with many software platforms, including Azure Quantum. We really want to engage as many people as we can in the community to really collaborate and develop this technology. And so I'll start by telling you about our quantum QCD architecture. This is what our H series quantum computer hardware is based on. QCCD stands for Quantum Charge Coupled Device. This is an architecture that was first proposed by NIST in Ion Storage Group back in 1998. So it's been a while. But the idea is that instead of having a long ion chain, we would have a device that can support lots of little bundles of ions. And these ions can be transported around on this device to different regions for quantum operations. So here's an example. This is our actual H1 trapped ion device. I know those electrodes are labeled, color-coded for the different zones. So blue is for operation zones. That's where all the quantum logic gates, initialization, and measurement happens. Then there are the green and the red zones that are for storage. And then there's a gray zone at the end. That's where we load the ions onto the trap. And so the advantage of this is that as we increase the number of qubits in the system, we can still maintain short ion chains and not have to deal with all these additional vibrational modes that come into play when you have a long ion chain. So that means we can have high fidelity quantum logic gates even as we add more and more ions into the system. And the other benefit of that is that there's very low crosstalk because your nearest neighbor qubit is actually pretty far away in the neighboring zone. So we use ytterbium ions for our qubit, and we use barium ions for sympathetic cooling. And currently we have two system model H1s on the cloud, and they're both running 12 qubits. There are a few special features on our systems. One is all-to-all connectivity that we get from physically transporting the ions. So they're not limited to just nearest neighbor interactions. We also have high resolution, single qubit rotations, so we can do these arbitrary angle rotations with very high resolution. And finally, we also have the qubit branching and mid-circuit measurement and qubit reuse feature, which means in the middle of your quantum circuit, you can measure just one qubit and then reset that qubit and put it back into your circuit for computation. So you kind of get the benefit of extra qubits that way. And on top of that, we can do conditional logic, which means depending on the measurement outcome of your qubit in the middle of your circuit, we can change the actual circuitry later on in your program. So it's like an if statement. If you measure 0, do this set of operations. If you measure one, you can do a different set of operations. And our H-series quantum computers are the only commercial quantum computers that have that capability. And it's really important because to do fault-tolerant quantum computing, you have to be able to do this conditional logic based on whatever error measurements you read out on your quantum error correction code, for example. And so everybody's going to have to be able to implement that. We already built in that natively into our H-series systems. So we benchmark our system using the quantum volume metric, which was first proposed by IBM. And the latest measurement on system model H1 is 1,024. That's the largest quantum volume ever measured on any system. And so 1,024 is 2 to the 10, so that's 10 effective qubits. These circuits are actually quite long. We have to run these random circuits. They average to about a little over 100 2-qubit gates, and you have to get reasonable answers after you complete those 100 plus number of 2-qubit gates, plus a lot of single qubit gates in between. So but you can see our average fidelities are quite good in the system, 99.99% for single qubit gate, 99.7% for 2-qubit gate, and 99.7% for measurement fidelity. And so when we first launched our first quantum computer back in the beginning of 2020, we had 4 qubits, quantum volume of 16 on system model H0. And at the time, we said 3 months later, we're going to get a record quantum volume of 64 with 6 qubits, and we did that right as the COVID hit. And that was the record at the time. And then this time last year, we also just launched system model H1, and we had the quantum volume of 128 at the time. But we've broken that record a couple more times. And so the latest one from the July this year was 1024. As you can see, the trajectory, if you plot along that line, is about a 10 times the increase in quantum volume every year. And so we hope to continue that trend and deliver more performance for the years to come. I just want to add that we also have a H1 emulator online now. It's not meant to be the fastest quantum simulator in the world, but what it does is actually have an accurate noise model built in that mimic our H1 systems. So you can use it to debug, to see what you can expect from in terms of performance from our H1 systems. And it's a great tool for researchers because you can see, you can tell where your noise is coming from, whether it's coherent noise or incoherent noise, or from qubit error memory or from gate error. So all those things you can, once you have that information, you can optimize your algorithm to actually mitigate some of the real errors that happens on the system. And so that also allows people to test, these the special capabilities such as mid-circuit measurement and qubit reuse. So it's a really useful tool for developers using the system. So I want to talk a little more about our technology roadmap for our H-series quantum computer. So so it kind of spans from H1 to H5 in a decade. As you can see, right now we are in H1, where all the the trap geometry is fairly linear. We have a few qubits. We're working on increasing number of qubits and increasing the fidelities of all of our operations. And it's one of the nice things about our system is even after it's built, we can do the upgrades as we go along. But moving forward, we're moving to this racetrack geometry for H2, and then to some kind of a 2D connected type of architecture for H3. and then increasing the size, and then tiling these systems together to get more and more qubits and zones. And so the idea is that we want to move from the NISQ era, NISQ type of systems where we're using physical qubits to a fully fault-tolerant quantum computer by the end of the decade. And for trapped ions, because we have such high fidelity in our operations, as well as the all-to-all connectivity, really the overhead for fault-tolerant quantum computing can be a lot lower than some of the other systems. So I think that's the advantage for trapped ions there. And so I want to show you the system model H2, our racetrack trap. So here's a picture of the actual trap fabricated by Honeywell. And you can see a little racetrack in the middle. And here's an image of ions loaded in the H2 trap. It's only half of the trap, you can see, because the full trap doesn't fit into the camera image here. And we can actually transport all these ions in the trap around the full loop. And here's a little video. You can see the ions going from zone to zone here around the racetrack. So that's a work in progress. You can see there are a lot more storage zones as well as operation zones compared to H1, which means more qubits and faster operations in comparison. And then if we look at going forward to H3, we're looking at a 2D connected architecture. And so we'll need junctions where we get ions to turn corners. So here's a picture on the right of one of the prototypes for these junctions that we built. And on the left here, let me see if I can play this video here, is you can see the ion moving into the junction and then coming out of the junction in whichever direction we want it to go. And so usually these the center of the junction is a little bit of a death valley for trapped ions, but we're able to design our trap and our waveforms very well so that you can see we can let the ions sit in the middle long enough to take these videos and not lose them at all. And so we can do these operations very consistently with very low ion heating and without losing the ions. So it's a great progress there. And then another piece of technology we'll need going forward is integrated photonic circuits. And so many trapped ion groups, such as MIT Lincoln Lab and Sandia and ETH, have made tremendous progress in the past few years in making these integrated photonic devices on the ion trap. We're still in the middle of developing these, but you can see here a couple of test chips of waveguides and beam splitters here. There's still, and then here are some just characterizations of what the beam profile looks like. There's still a lot of work to be done there before we can really fully integrate that into the system and make it scalable. But I think it's looking very promising there. And so as these systems come to some level of maturity that's ready for release, then we will definitely make that available for people to use. And so algorithm developers will get their hands on these devices at the first opportunity that we can provide them. And so that's where, I guess, Azure Quantum, partners like Azure Quantum comes in for these systems.
Perfect. Thanks, Patty. Thanks, Patty, and thanks so much to Quantinuum for having us join the talk today. My name is Jeff Henshaw. I'm a director of business development with Microsoft's Azure Quantum team. And we're really pleased to be here because this set of talks represents some pretty amazing partnerships that are really helping advance the state of the art, the state of the technology, and the state of the business in quantum computing. So it's a real pleasure to be here with Quantinuum, formerly Honeywell. At Microsoft, our mission is very simple. We want to empower every person and every organization on the planet to achieve more. And the reason most of us are participating in the quantum community is that many of those challenges that we want to achieve more on are beginning to bump up against the limits of classical computing systems. And a theme that we've seen at the event this year is that the industry collectively doesn't know when commercial viability and true scale is going to arrive in systems. But it's a thrill for all of us to be participating in the evolution of those systems and really pushing the envelope, including the H-series systems that Patty shared with us. And it's a very exciting roadmap. Where Microsoft comes into play is with our cloud. The Microsoft Azure cloud, depending on who you are and what your role is, you probably participate with Azure in one of a few different ways. If you're a consumer, you're probably enjoying cloud services, whether it's OneDrive cloud storage, Outlook email. If you're in an enterprise, you may have an enterprise agreement where your enterprise IT is hosted on Azure. If you're a developer, you're probably using GitHub or Microsoft's Power Analytics platforms. But these are all a part of a global cloud, we think is an exciting global footprint for Microsoft. And we're very excited to see the diversity of usage, whether it's individuals, enterprises, and even governments around the world, putting these cloud services to work in unique and different ways. From a developer perspective, Azure includes a suite of services from compute to storage to AI to ML. And we view quantum as part of that family of services. And one of our goals is to enable developers to use quantum technologies, including Quantinuum's H platform, in the development of solutions that are probably going to be leveraging lots of different types of cloud technologies. So we're excited to have Azure Quantum bring an ecosystem together in a consistent way that lets you leverage all of these technologies to build the right solution for you. Azure Quantum in particular is a hardware agnostic single marketplace that allows a developer to write code once and run it on a variety of systems. We're language agnostic, so you can bring your existing code. If you have an investment in Python, if you have an investment in other frameworks, we want to openly invite those frameworks so that you can leverage the investment that you've already made as a quantum algorithm developer. If you're new or just getting started or wanting to scale up those algorithms to more complex systems, I think the further out we go on that H-series roadmap, the more algorithmic scale we're going to be able to achieve. We have a language called Q# that was designed from the ground up to abstract some of the basic fundamental physics in your quantum algorithm development and let you think at a higher level on the problem that you're trying to solve. Again, we want you to be able to write once and run on any platform, whether you're writing in Q# or an existing framework, and give you great choice of platforms to run on. And finally, as I mentioned earlier, we want to have seamless integration with other Azure services. So if you need ML services, if you need AI involved in your overall solution, and quantum is just part of that solution, quantum will accelerate the quantum appropriate workloads in your solution while you're using other Azure services for the workloads that are more appropriate for those services in particular. We've had great success to date, and we're really, really proud of the partnerships that we formed. You'll notice Quantinuum up on the top line there, which is really our focus today, but we have a suite of partners in both hardware and software platforms powering the Azure quantum ecosystem. And our goal with these partners is to always provide you, the quantum developer, with the latest, fastest, most scalable quantum solutions in both hardware and software that's available at any time on the market. And that's why the H-series roadmap is so exciting to us, because we'll be making that H-series available to developers around the world as it matures, making sure that you're always current and you're working with Quantinuum's latest technology. We've had some great success with customers using the system and beginning to train their workforce on quantum algorithm development and techniques. And we've also got an incredible network of university and consortium curriculum partners helping us build the right training materials, the right curriculums, the right tutorials, the right coding competitions, to make sure that we're bringing up a quantum savvy workforce that'll be able to engage the software, hardware, and development techniques that are coming to market on modern quantum systems like Azure Quantum. We've recently been deploying a program called Azure Quantum Credits. And the goal of Azure Quantum Credits is to make sure that cost is never a barrier to people that are looking to innovate, especially in research and university settings where the cost of these systems might otherwise get in the way. We want to unlock that for people. And so we've announced an Azure Quantum Credits program. It's $10,000 blocks of credits. They're granted to research work going on, including in academia, to help unlock use of the system to begin scaling algorithms to have commercial impact. And we review the potential impact that we see in our applicants and award those based upon where we think the greatest impact might happen. We've had incredible uptake on this already, so we're going to be continuing the program into 2022. And in the coming weeks, we're going to have some announcements about interesting and exciting ways that we're going to be expanding this program. Because while this is a business, we want to make sure that cost is never a barrier to innovation, especially as the quantum industry is evolving as rapidly as we're seeing at Q2B this year. So you'll notice that this includes support for all of the major SDKs. We've built this credit program in a very open way. You can use the frameworks. You can use the services on Azure Quantum. They're going to be most interesting to your algorithm development, and we really encourage people to take advantage of this. With that, I'm going to turn it back over to Patty, who's going to wrap up the talk with a focus on how Quantinuum and Honeywell's initial hardware and Azure Quantum have worked together to enable customers and middleware providers to build on top of the hardware and cloud service platform that we partnered on to deliver real solutions with real impact today. So back over to you, Patty. Thank you, everyone.
Thanks, Jeff. So in this example here, we have Cunesis working on quantum simulation of molecules. And they're looking at calculating vibrational modes of water and methanol molecules, and then comparing the results from the quantum computer to the known value of the system. And so they have a paper out here that basically shows you how to translate the molecular problem into a quantum circuit. And so there are actually two stages. First is using a variational method to calculate the vibrational modes. And so this part is actually done on a classical simulator using some of the Azure Quantum resources. And then on the second part of it, though, once you have the vibrational modes, then you can use this Hessian matrix to calculate the energy of these vibrational modes. And so, that second part was done on the on Honeywell's or Quantinuum's H1 trapped ion quantum computer. And so here are the results from their study. And you can see this is for water molecules, the first three levels. The calculated ground state energy comes very close to the actual measure, the known value for these levels, and it's accurate to within a couple percent. For methanol, this is a much more larger molecule, so a lot more complicated. And so they calculated the first 12 vibrational modes in the system. And as you can see, the accuracy from our H1 system is still quite good compared to the exact value. So that was a pretty nice, pretty amazing demo that they did at Cunesis. And so with that, I just want to say, hope all this information is inspired you all to think of ways you can use our H1 trapped ion quantum computer and our future generations of our H series systems. And you can find out more information, and the latest news at our website at quantinuum.com, as well as you can get all the software developer support from Azure Quantum as well on the Azure Quantum site. And I just want to point out that there are a couple exciting talks following this talk. At 10:30, there's a talk on quantum intermediate representation that Microsoft is spearheading, and it is in another session. But we'll also include some demos from our Quantinuum system model H1, demoing results running program using QIR. So that should be pretty exciting. And also, there will be a session at noon today from Kieran Ryan Anderson with the latest results on our quantum error correction work at Quantinuum. And so there you can also see get a sneak preview of our hybrid computing capabilities that may be coming soon on our H1 system. So thank you.
We have time for a couple questions.
All right, we have time for questions.
Any questions? Going once? Yes.
Maybe one question on this integrated photonics. So can you maybe extend a little bit on kind of what kind of capabilities you get additionally and what are the challenges in building these?
So the capability, what we need to do right now, we have these lasers. We're using lasers to control these quantum operations. So initialization, measurement, quantum logic gates are all done with lasers. And so what happens right now is we have these laser beams shooting into the ion trap coming from everywhere. They're sensitive to vibrational noise. But if we can use these photonic integrated devices, then we can actually deliver the beams right onto the trap, really close to where the ion is. And so you get at least a lot of mechanical stability, a lot more control over those beams. The challenge there, though, is that these ions tend to like UV lasers. So for example, ytterbium has a wavelength at 369 nanometers. So that's probably the hardest wavelength to hit. Some of the material may not have band gaps down that low. So those are the challenges in dealing with materials in terms of fabrication and making sure those photonic devices are low loss, can handle the power, and then deliver the power to the right place.
Other questions? Yeah. All right, enjoy the next sessions, everyone, and thank you so much for joining us.